video, the recording, and let me welcome everybody to the EC Game Changers series. Today is the 37th seminar on almost 50 years of coronal heating, given by Joan Schmelz. This is the second part of the Game Changers series, which concentrates on scientific themes, today on coronal heating, after the first series of the first part of the series, which concentrated on missions that changed the game in the space sciences. All talks are recorded and online on the EC webpage if you want to go there and peruse the 36 talks given earlier. The next talk, by the way, will be in 1 week from now, same time, on testing the massive black hole paradigm with high-resolution astronomy, and it will be given by Reinhard Genzel from Max Planck in Garching. Now, to today's talk, it is my great pleasure to welcome Joan Schmelz. Joan has a bachelor and a master from Rensselaer Polytechnic, which is in upstate New York, from where she moved to Penn State, where she got the PhD on extragalactic, where she got the PhD with a work on extragalactic hydroxyl. After her PhD, she went to NASA and worked 5 years at Goddard, where she was in the team of the Solar Maximum mission. And after that, she had an assistant professorship at Rhodes College in Annapolis for 4 years until she found her alma mater, where she worked for more than 20 years as a professor at the University of Memphis, where she was heading the solar physics division. Her research was on observations of coronal loops and on developing constraints on coronal heating models. That's why I thought she would be a great speaker for today's theme. She was mainly working on the sun, but also on many other astronomical objects using data from ground and space-based observatories in almost all of the bands across the electromagnetic spectrum. In 2015, Joan switched gears and she became the deputy director of Arecibo Observatory, the poor observatory, hurricane-battered observatory, which ultimately collapsed last December. And I'm sure, Joan, your heart must have been bleeding to watch that happen. But already in 2018 and 19, she moved on and was the assistant director of the SOFIA telescope, and responsible for science and public outreach. That's the infrared telescope on a 747 flying in the stratosphere. And today, Joan is the director of the NASA postdoc program at USRA, which is the University Space Research Association. Joan has also served in numerous capacities for the community. She was chair of the USRA Diversity, Equity, and Inclusion Committee. She's a former vice president of the American Astronomical Society and a former chair of Status of Women in Astronomy. In 2015, Joan has received numerous awards. In 2015, she received an award from Nature, who honored her as one of the top 10 people who made a difference. And this honor she got for her work to fight sexual harassment in the scientific community. But closing the loop back to her earliest year at Rensselaer, she already got, as a master student, a teaching award from the Rensselaer Polytechnic, which testifies her outstanding science communication skills, which I had the pleasure to witness several times at COSPAR and at many other conferences. And I'm looking forward to witness that once again today, when Joan will tell us about almost 50 years of coronal heating, almost meaning it dating back to Parker's seminal paper on topological dissipation and the small-scale fields in turbulent gases, which appeared in APJ in 1972, almost 50 years ago. So Joan, thanks for joining us today, and the floor and the screen is all yours. We're looking forward to your talk.
Well, thank you, Rudy, and thank you, everyone. I'd especially like to thank Rudy for the title, which I had not realized it was almost 50 years of coronal heating until he told me. So solar physicists agree that coronal heating involves the sun's magnetic field, but they disagree on all the details of how the magnetic energy is transformed into thermal energy. Theoretically, it's easy to heat the corona. The plasma density is low, so the energy required is small. That means that there are many coronal heating models, but the details that make one different from the others operate on such small scales that even next generation technology can't hope to resolve them. This dilemma means that observational constraints are few, so that normal back and forth of the scientific method didn't work here. Models explaining observations and making predictions, observations confirming some models and challenging others, just really never happened for coronal heating. Modelers had a monopoly, which led directly to the subtitle of this talk, that coronal heating is the longest standing unsolved mystery in all of astrophysics. But this situation, which was the status quo for decades, started to change with the launch of EUV imagers in the 1990s, when solar physicists like me were really surprised to see loops dominating the images. So here's a very dramatic example from TRACE, the Transition Region and Coronal Explorer. Up to this point, loops really played no role in the coronal heating problem. Observations told us that loops were in hydrostatic equilibrium and loops resulted from steady, uniform heating. But the inset here shows the observations on the top and what we expect from hydrostatic equilibrium in the bottom. The trace loops have super hydrostatic scale heights, really serving notice to all of us in our community that the collective knowledge of coronal physics might need to be revised. Because these EUV imagers like TRACE could also measure temperature and density, results began to appear in the literature that were just not consistent with this steady, uniform heating. And that the results, the modeling results that really had been the standard since the days of Skylab. So these controversial results fell into three categories: overdense loops, long lifetime loops, and multithermal loops. And these results led to a series of coronal loops workshops where the relevant players met in beautiful places to sort out the controversies. So these are some of the early ones that I went to, but the loops workshops are still going on, telling us that not only do solar physicists like beautiful places, but that loops are also controversial and coronal heating is still not a solved problem. So let's finish this introduction with just some jargon. A loop is a distinct configuration in an observation, and a strand is a fundamental flux tube where the temperature and density are constant, perpendicular to the magnetic field. So a loop could be composed of a single strand or many unresolved strands. And this is the jargon that we adopted early on in the loops workshops. So we were all talking about the same thing, because otherwise one person's loop was another person's strand. So we're going to begin with controversial result number 1, overdense lubes. And this is a list of early references on the topic. But to get to density, you first have to start with temperature. So let me walk you through the analysis. So you pick your favorite loop, and this is a trace one. It's on the disk. We're looking at an image in the 171 angstrom filter. That filter is centered on a strong iron line, and you select a group of pixels along the loop, like we have here. Then you look at the exact same loop with the same pixels in a second filter. This one is 195 angstroms. It's centered on a hotter line, and these two images are sensitive to temperature. So the way it works is that the intensity in one of those pixels that you chose is proportional to the integral of the response function times the electron density squared times the path length. And that response function is, you can think of it as the sensitivity of the instrument as a function of temperature. So because we have two different filters, we can do this, we can use this equation for both of them and then put them together. So in the first case, we're assuming an isothermal approximation, that the plasma in your pixel is isothermal. This was the state of the art early on. No one had considered the possibility that a single pixel in a loop might have more than one temperature, because a loop was thought of as a flux tube, and the material inside the flux tube came into equilibrium very, very quickly, much more quickly than your measurement. So isothermal approximations were the state of the art. So if that's the case, you can pull the response function out of the integral, and the integral NE squared dl is defined as the emission measure, the amount of emitting plasma in your pixel along your line of sight. So then your equation is really quite simple, the response function times the emission measure. So the response function is a property of your instrument, and the emission measure is a property of the sun. So there's two filters, 193 and 171. Again, two different lines, iron lines, and we can divide one by the other. So on the left-hand side would be the measured intensity ratio from your observations, the response functions, and the emission measure is a property of the sun. So that, see, there we go. That gets crossed out, and your observed intensity ratio is just a function of the response function ratio. And here's an image of that, where the black solid line is the response function ratio, and we're plotting it as a function of log temperature. The red plus sign is the observed ratio, and where those two intersect gives you the temperature. So you just drop down and look at the x-axis, and you end up with a temperature just over 1 million degrees, 1.2 million degrees. So you do this for all your pixels along your loop, and then you compare them to what you expected, which are the results from Skylab, and you get something that's very different. So in this plot just takes a little bit of explaining. It's the temperature along the loop, but on the y-axis, but it's normalized to the peak. So, and on the x-axis, it's the loop half length. So in the upper right-hand corner, it's the peak temperature of the top of the loop, and then everything's normalized with respect to it. So the solid thick line, which is labeled RTV, that's Rosner, Tucker, and Vienna. Those are scaling laws that were developed with observations from modeling and Skylab loops. And that's what everyone expected. But the thin lines are the results from many trace loops. And your eye is drawn to some of those points that sort of drag down to lower levels. But if you look in the upper left-hand corner, you see that there are dozens of loops that are extremely flat, that are essentially indistinguishable from that upper axis. And some of these data points don't have error bars on them. So it's possible that a lot of those points that you see with the little labels on them at the end are actually just have big uncertainties. So the results were that these temperature distributions were flat, very, very different from the expected RTV scaling laws. And absolutely everything that could have been wrong was investigated as a result of this, because it was so controversial. It was so unexpected. So once you have temperature, then you can go and find density. And the way you do this, you go back to that intensity equation, which is just the response function times the emission measure. You solve for the emission measure, and then you remember the definition of emission measure and assume that the path length is equal to the loop width, solve for the density, and with observables. And you get a similar controversial result. So in the scaling laws of Rasner, Tucker, and Vienna, that result, the plot, depends on the length of the loop. So the solid lines are the expected results, and the thin lines at the top are for the dozens of trace loops that were observed. And you can see that all of those thin lines are indicating that these loops are more dense than expected. So this is the controversial result of over-dense loops that began to appear in the literature. The second controversial result was long lifetime loops. And again, these are some of the early results from Amy Weinberger and Harry Warren and their students and collaborators. And in this one, you take advantage of the fact that instruments like TRACE make movies, beautiful movies, so you can follow the evolution of the loop as it grows and evolves and changes. And one of the things that these authors noticed is that the loops were cooling, and you could watch them cool through the different filters. So here are the response functions for the 3 different coronal filters on TRACE. The orange one is the coolest one. That's the 171 angstrom filter, and it's centered around a very bright iron 9 line. The yellow one is 195, again, centered around a bright iron 12 line. And then 284 centered around a bright iron 15 line. So you can see that the peaks, they're not just the peaks, because there's lots of other things that creep into the filter. But overall, we're looking at 171 being the coolest, 195 being the middle one, and 284 being the hottest. And then what they did was they watched loops evolve and cool and appear first in the warmest filter, and then in the middle filter, and then in the cooler filter. So here's just a picture from one of their papers, and the loop is outlined. And if you watch lots and lots of movies of trace images like they did, you can actually see this happening for many, many, many different loops. And then you can measure the lifetime of these loops as they cool. So what they did next was plot the intensity, essentially a light curve, the intensity on the y-axis, the time on the x-axis. And you can see that the loop first appears in peaks in the warmest filter, that 284. It then starts to fade out in 284, and then you see it at a later time in 195, the middle filter. And then even later, you see it in 171, the coolest filter. So you could watch the loops cool, but you could also measure its lifetime. And then you could try to model that loop using hydrostatic equilibrium. And the results failed miserably. So in this point, or this plot, the dots are the observations of the trace intensity. And the dashed lines are what you would expect from the models. And if the loop were in really a single flux tube, one single strand or thread, you would get one of those little peaks, little dashed peaks. And your conclusion would be that this doesn't work because my loop lifetime is so much longer than the model lifetime. So they realized that this was a significant problem. And what they ended up doing was assuming that the loop was composed of multiple strands and that each of these strands could be cooling independently, so that within the observation, within the observed loop, there were many different strands separated physically by the magnetic field, and that the plasma inside those strands could evolve differently and separately from the others. And that's the only way that they could find to explain this long lifetime loop. And you see here the series of dashed curves of different loops cooling at different rates. And then we get to loops with multithermal cross sections. And this is the part of the controversy that I was involved in from the very beginning, and really didn't even know about the other results that were happening simultaneously until we all got together for that first loops workshop. But let me walk you through some of our early analysis and how we came to really understand that loop cross sections were multithermal, and that loops, the only way to explain it was that loops were composed of strands, so that loops had substructure. So if we go back to that original equation for the intensity, and in this case, we're dropping the isothermal approximation. So we cannot do that first step that makes it easy by pulling the response function out of the integral. We have to leave it in there. But we're going to change it from a length integral to a temperature integral. So instead of having NE squared dl, we're going to change that to DEM dt. And DEM is the differential emission measure. So our intensity equation looks like this at the bottom. So, and the differential emission measure is, if the emission measure is the amount of emitting material, the differential emission measure is the amount of emitting material in a particular temperature band. So it turns out that the analysis is much more difficult and much trickier. And that's part of what I started working on at the University of Memphis with some of my undergraduate students. And this is a really nice little program that I'll walk you through called DEM Manual, written by one of my students, Jason Kimball. And this is just an example of how it works. So on the left-hand side, you get the differential emission measure plot. So we've got log DEM on the y-axis and log temperature on the x-axis. And the red spike, that's what would look, that's how we would represent an isothermal plasma. So there's emission measure in one single temperature band. And then on the right-hand side is the error analysis. So this is the ratio of the intensity predicted by our model, in which case, this case, it's that red spike on the left. And it's divided by the observed intensity from the instrument. And these are data from ICE, the EUV imaging spectrometer. And ideally, what you would want is all of the different data points to be up there at around a level of 1 within the uncertainties. And in this particular observation, there were multiple lines, several iron 12 lines, iron 13 lines, iron 14, 15, and 16. And you can see that this is a terrible fit to the data, that not only do we see all of these different points that don't intersect with that dashed line at 1, but in the upper right-hand corner, you can see the reduced chi-squared, which is almost 60. And ideally, you want it to be close to 1. So if this is the best isothermal fit that we can get to these data, the next step is to drop that isothermal approximation and allow emission measure to be in more than one temperature band. So here's an intermediate step on our way to the best fit. So you can see that on the left, we no longer have a red spike. We have emission measure in a couple of bins. And you can see how much better the plot on the right has gotten, right? So we now have a lot of the points within 1 sigma of 1. So the predicted to observed intensity ratio is close to 1. And our reduced chi-squared has come down from almost 60 to 3.6. But it's still not really good, because you can see that that highest temperature line, that green point for iron 16, is still pretty far off. So this is now our best fit, that we have almost all of our lines, or all of our lines are within about 1 or 2 sigma of 1, and our reduced chi-squared is 1.3. And try as we might, we can't get it any better than this. So the reason it's not perfect is because the sun has a mind of its own and we don't understand everything. And inherent in all these results are atomic physics that we know change and improve as time goes on. So if we redid this with the atomic physics of 10 years from now, we would hope that some of these small glitches would diminish. But in this case, this is about the best we can do. And a reduced chi-squared of 1.3 is enormously better than 60. So our results indicate that the plasma can't be isothermal, that it really needs to be multithermal. And in order to do that, the loops have to have substructure. Those loops have to be made up of strands. So then we come to the flowchart. And this is something that was put together by my colleague, Jim Klimchuk, at the 3rd Coronal Lubes workshop back in 2007. And this was a way to try to put all of these controversial results together. And we're going to take it one step at a time, one question at a time. And starting at the top, where it says in blue, there's a box that says overdense loops. So remember, that was the first thing we talked about. And there's a decision. If there are overdense loops, and the answer, if there are no overdense loops, if the question is, are there overdense loops? And the answer is no, then isothermal loops are okay, steady heating is okay, and we go back to those Skylab related results and say everything's fine. But if the answer is yes, then that steady heating just doesn't work, and we might have to go to impulsive heating. So after seeing this flowchart, my students and I tried to find a loop or a set of observations that we could take all the way through the flowchart. Like up until now, all of those different results that we've talked about so far had been done separately. They were done like stovepiped, like we were not necessarily talking to each other about our results. So this is the loop. You can see it's a series of images, and they're color-coded. In the top left is the warmest one. This is an X-ray image from the X-ray telescope. And the little arrow is pointing toward what we started calling the flowchart loop. And then going down to orange, yellow, green, through the colors of the rainbow, you can see the loop in with the little arrow. And you can also tell that these images are not taken simultaneously. Like the flowchart loop doesn't appear in all of these images at the same time. And the reason is because it's cooling. So it's going to appear in the hotter images in the upper left much earlier than it would in the image in the lower right, which is the coolest filter. So we're going to use this loop and go through the flowchart and compare the results to some of the things that you've seen before. So remember this plot from a while ago, right? It's got the RTV thick lines and all the trace results from the thin lines. So we did the exact same analysis for the flowchart loop using the AIA filters that are closest to trace. And our results, oops, I think, yeah, there we go. I realized that what happens is that I did not take out the animations in these images, and that you're not going to be able to see the animation. So normally this little red line at the very top would appear, but it's not going to. So it's going to be just a little bit kludgy. So I apologize for that. But I think that's a zoom feature. I'm not sure how to get around it. But the red line is the results for the flowchart loop. So what it's saying is that the flowchart loop is getting the same kind of controversial results for flat temperature distributions as all of these trace loops did. So then once we have that, we can go on to the density. And I think I'm going to have to do this funny thing again. So just bear with me for 1 second. Okay. And there is our red line for our flowchart loop, right in the middle of all the trace results, and very different from the results that are expected from the RTV scaling loss. So in the very first step of the flowchart, we take a look at the question that says, is your loop overdense? And the answer is yes. So that means that the loop cannot be heated in a steady manner, that it's really impulsive heating that's happening. So then we're going to go to the next question. Oops. And that next question is in blue, and that is your observed lifetime equal to the expected cooling time? If the answer is yes, then your isothermal loop is okay. It's just that your heating is dynamic. If, on the other hand, if the observed lifetime is much greater than the cooling time, then your loop has to be multi-stranded. And just reminding you of those results from Warren and Weinberger that we've already just talked about. Okay. So then we made movies of our loop. And in the case of AIA, we had 4 different filters. We had a very cool filter that's in purple here, centered around a 131 angstrom iron line. We had 171, the same as trace. We had 193 in green here, the same as trace. And then we had 211, which was an iron 14 line that's in yellow. So these are the response functions, and what we would expect if this loop were behaving in the same way as the trace loops is that we would see it in the purple filter, we would see it in the yellow filter first, and then green, blue, and purple as the loop cooled. And that is indeed what we did. We made movies of the loops in all of these different filters, and we made light curves based on the movies. So we just have the intensity as a function of time. And you can see that first we see it in the warmest filter, that's iron 14. Then we see it in the green filter, and then the blue, and then finally in the purple. And then we measure the loop lifetime And the way that they measured the loop lifetime in the original papers was to take the half height of the coolest filter and then the half height of the warmest filter, and then find the observed lifetime, which in this case is greater than 1.2 times 10 to the 4th seconds. Then with the radiative loss function as a function of temperature, we can find out what the expected loop lifetime is. And our radiative cooling time of what we would expect is about 1.67 times 10 to the 3. Our observed lifetime is almost, but not quite, an order of magnitude greater. So once again, with our flowchart loop, we find that indeed the observed loop lifetime is much, much greater than the expected cooling time. So our loop cannot be isothermal. It has to be multi-stranded, very similar to the Warren and Weinberger results. And then our last step is is the loop multithermal? So this is the analysis that I described earlier that my students and I had been involved in. And if we can indeed show that this loop is multithermal, then everything in the flowchart is consistent. But if it's not, then we have to go back to the drawing board because there's something that we're not understanding. So we took our flowchart loop and we did multithermal analysis. This is a wonderful program written by my colleague, Mark Weber. It's called DEM Iterative. And it's a complementary program to DEM Manual, which I showed you earlier. But the results turn out to be the same. It is the best fit is a multithermal, that's the black curve. And it's a series of, actually it's not a curve, it's a series of histograms, one in each temperature bin. And then it's iterative because it will change the intensities of your lines within the uncertainties and then redo the result. So the series of red dashed histograms gives you an envelope for how good you think the fit is in that particular temperature bin. So this is the universal feature that the fit is always tighter at the peak. And as you get to the edges, both the hot temperature side and the cool temperature side, the uncertainties get bigger and bigger. And this is on a log-log plot. So it's mostly the stuff at the top that we're interested in. But one of the things that this tells us is something we're going to talk about in just a little bit if we have time, and that's what happens on that very high temperature side. So in terms of the flowchart loop, it is indeed true that the loop is multithermal and that we have consistency. So we've put all of these results together, and what we were looking for and hoping for is some kind of observational confirmation that our ideas, our models, our concepts about multithermal loops with substructure were really true. And that came in the form of some rocket observations from in 2012 from the High-resolution Coronal Imager, which finally provided this confirmation of loop substructure. This instrument has the nickname of High-C. It's a sounding rocket payload. It's designed to take high-resolution images of the solar corona. And we have a comparison image on the left. It's from AIA. That frame has a resolution of approximately 1.2 arcseconds. Compare it with the same field of view on the right from High-C with a resolution of something like 0.3 arcseconds. And if you look at structures sort of right in here, where my pointer is, right in here, you can see that indeed this feature has substructure. And not only that, but the strands appeared to be braided and tangled. And Hi-C made movies, and you could see actually a small energy release as the tangled strands reconnected. So it was the first time we were able to show directly that magnetic reconnection in these braids was happening, and which may be a major source of coronal heating. And that leads really nicely into the last topic, which is hot plasma. And it was, for me and my results, it was inspired by these Lubes workshops that I got the idea to work on this project from talks that were given there, which is exactly the kind of thing that you want a workshop to do. So there are two different and competing overall models for coronal heating. There's wave heating is the first one, and that's MHD waves are produced by turbulence in the convection zone. The waves travel upward, dissipate in the corona, they deposit their energy in the gas in the form of heat. The other method is magnetic heating. So the magnetic energy is continuously built up by photospheric motions and released through magnetic reconnection in the form of large flares, but also in smaller events, usually called nanoflares. So these are the two main heating mechanisms that when we mentioned earlier that theoreticians kind of had a monopoly on the coronal heating problem, this is what we meant. This is the case where the modelers could really compete against each other and have very little input from observers until this time that we've been talking about, this pivotal time when the EUV imagers really started playing a role. So these methods are sometimes nicknamed AC and DC. So AC is this foot point shuffling, it's the MHD wave propagation, and then the predictive element of these models is something we're going to focus on, that it's very challenging for these models to produce hot plasma. And hot plasma, I'm talking about something like greater than 5 megakelvin. So on the other hand, the DC models, these are the magnetic field stressors, they're produced by reconnection events. So they're like little flares or mini flares or nano flares. And it turns out that this hot plasma, this greater than 5 megakelvin plasma, is a natural consequence. So if you can observe the 5 megakelvin plasma, it is a prediction of DC models, and it's very challenging to produce for AC models. And the reason is that, well, in both cases, the energy is supplied by these photospheric motions of the foot points. But for a given foot point velocity, those DC models predict lower average heating rates, but greater temperature variability compared to the AC models. So the evidence of the hot plasma is greater than 5 megakelvin in the cores of active regions could be one of the ways for current observations to distinguish between these two categories. So an easier way of saying that is the hot plasma is a natural consequence of nanoflare models. So we started to investigate what current observations could tell us about this hot plasma. So we selected a series of active regions. They were selected with the X-ray telescope, and they also had images in cooler filters from AIA, from the Atmospheric Imaging Assembly. So we combined X-ray images and EUV images of a host of active regions. And we used that program, DEM Iterative by Mark Weber, to try to understand what was going on with the hot plasma. So in this case, we don't really care about this cool stuff over here where my arrow is pointing. And that's where the uncertainty, you can see that the red histograms get wider and wider. And if we were, and we can kind of ignore that because we're really interested in what's going on over here. So you can see, as we said earlier, up at the peak of the differential emission measure curve, those red histograms really cluster, they're really very tight. And as you move over to the hot side, they're still pretty tight, but then way down here, they sort of loosen up. So this is where your uncertainties are really dominating your results. So if we do a straight differential emission measure like this, it's hard to answer a question, is there really significant hot plasma in this quiescent active region with temperatures above 5 megakelvin? But one of the ways to do it is to look at the error analysis and then sort of truncate the DEM curve at 5 megakelvin. So let me take you through that. So here's our best results. And here is the error analysis, right? So there are several different filters from AIA. They're in blue. There are 3 different filters in this particular observation from the X-ray telescope. They're in red. For reasons that no one is quite sure about, this line over here, the very coolest one, is always off. So it's quite possible that there's something missing or uncalibrated about this filter. But because that's the cool end, and we don't really care that much about it for this project, we're going to ignore it. It's also what leads to the high value of chi-squared up here, 2.8, where everything else looks really good. So here, it's a very good fit to the data. All the data points except this one are within one or two standard deviations, and everything looks really good. So then what we're going to do is we're just going to take our original curve and we're going to artificially truncate our differential emission measure curve. So we're going to say, in our model, we have 0 emission that's greater than 5 megakelvin. So can we explain our observations with a model like this? And the answer is no, we really can't, because look what it does to our error analysis. So most of the cool stuff stays exactly the same because that part of the differential emission measure curve hasn't been affected. But when we drop precipitously that higher temperature emission measure, all of our high temperature points drop way down here below 1, very far from the line where we want them. And our reduced chi-squared goes way up to 58. So this was the best way we could explain or describe or observe the hot plasma at the time with those observations. But right now, we have a rocket payload called the Marshall Grazing Incidence X-ray Spectrometer, or MAGIX. It's a sounding rocket instrument, and the planned launch is later this month. Right now, the schedule is for July 30th. And unlike any current instruments, it is super sensitive to that hot plasma in active regions that would be produced by nanoflare models, the kind we were really struggling to find with the analysis that I just showed you. And it's also designed to determine the heating frequency in these active region cores by observing them in a series of forests of high temperature spectral lines. They're the spectral lines that were part of the solar maximum mission back in the 80s. They're the spectral lines that are used by astronomers in instruments on Chandra and XMM. And right now, solar physicists are just blind to this part of temperature space. But with MAGICS, hopefully we'll keep our fingers crossed for a successful launch later this month, and we'll have data finally on the sun again in these hot temperatures. So let me summarize and then just take you through the conclusions. So we have this legacy from Skylab, where loops are flux tubes, the plasma is in hydrostatic equilibrium, the temperatures and densities are determined by scaling laws, and this Rosner, Tucker, and Vienna paper sort of ruled the day for decades. But in the 21st century, we found that the densities are much, much greater than the predictions of scaling laws, that the lifetimes are much greater than the predicted cooling times, that loops appear to have multithermal cross sections, and none of this is consistent with RTB. So where does that leave us? Well, the good news is that observations are finally starting to contribute to the coronal heating problem. The coronal loops appear to be multithermal and multi-stranded, and that those results appear to have been confirmed by the observations from high C. That hot plasma appears to be common and widespread in active regions, and we're waiting for MAGICS to confirm that. But all of these results provide observational constraints that any viable model of coronal heating will have to explain. Thank you very much.
Thank you, Joan, for this very nice and very tutorial overview of the coronal heating problem. I, for one, learned a lot, and I was reminded of many things I should not have forgotten. So, yes, this was an outstanding and tutorial talk, but I'm sure there remain questions open, and we have a very good audience. Now, the audience has two ways to ask their questions. First, you can type them in the chat, and I will monitor the chat and read them to Joan. And or you could raise your electronic hand, and I will try to watch these windows simultaneously, but Willy, you will help me telling me when electronic hand has been raised. And then Willy will open your microphone and you can ask your question directly. Let me start with the chat. First to read it. Oh, a very brief question. Probably, I'm not sure if it can be answered at this time with the observations at this time by Zakaria Pine-Meyer. The strands making the substructure of the rules. Do these strands have fractal behavior? Can you say anything about that, Joan?
I really can't, because the only real observation of the strand that we have is from that one observation from high C. I think we're looking forward to future launches of high C so that we can learn more and more about these strands, which right now, from all these results that I've talked about, we're just inferring that substructure because we need it to explain the results. So stay tuned.
Right. Yeah, there's way too few orders of magnitude over which this can be mapped. So fractal behavior needs several more orders of magnitude to be able to answer this substructure of the loops. The next question is by Ari Lau. Is there evidence for a power law contribution to the Maxwell-Boltzmann distribution? Is there evidence for a Kappa distribution?
So it's whenever these controversial results first appeared in the literature, one of the things that happened is that everybody in the community tried to shoot it down, right? They tried to explain it away in some way. And one of the ways that my colleagues at the Coronal Loops workshops wanted to explain away the multithermal distributions was with Kappa distributions. And they said, if you just stop using these, these regular ones and use Kappa distributions, all these results would go away. And then much to the credit of the person who made that critique, he came back to me several years later at a Lubes workshop and said, we tried it with Kappa distributions and the results just got more multithermal. So I think that at least for the Kappa distributions did not address the multithermal question. They did not make it go away. So I think we're still left with these 3 or 4 different really strong observational results that have persisted through a couple of decades now. And we're still trying to explain them with something other than substructure.
Let's take one more question from the chat and then switch to the raised hands. Next question is by Richard Marchand. In models, is a loop assumed to be equipotential? Is there evidence of significant electric fields? If so, what would be the effect?
So, Rudy, significant galactic fields?
Electric, not.
Okay. So the models, this is not my area of expertise, but the models are extremely sophisticated. They sort of one up each other in every possible way. But I think that everything involved has been inserted. But in terms of the loop models, the originals were hydrostatic equilibrium and steady heating, and now all of those assumptions have been taken away and more sophisticated elements have been put in. If we're talking about coronal heating models, then they are even more sophisticated. So they can really get to the point where they can create their own flares and things like that. So again, not the right expert to ask that question. Okay. And Rudy, maybe you know.
Fair enough. Now let's switch to the raised hands. I think I can see one by William Wall. Willie, could you open the microphone, Bill Wall?
Hello, can you hear me?
Yes,
am I coming through?
Can hear you.
Okay,
Hi.
great. Hello. I really like the way you organized the talk. It was nicely done. There are a couple of questions. One is that I'll put together. They're related to each other. Are there any large-scale variations across the surface of the sun, say from the poles to the equator, in the physical properties of these loops and their strands? And could such physical variations, such large-scale variations in those properties, provide insights into the heating mechanism?
I'm not aware of anyone that's really tried to do something from the poles to the equator. A lot of times, so I'll give you one of the observational constraints about this. In the early days, there were a lot of people, including me, that were asking the instrument scientists for an isolated loop that we could study. And they would come back and say, you people don't know what you're talking about. There's no such thing as an isolated loop, right? The sun is just more complicated. As you can see, even in this image, it's like, which loop would you want to select? So there's a couple different ways where you can go and choose loops. One is if you have some really good software that identifies different kinds of features, almost like facial recognition software for loops. And people are doing that. The other thing is the mechanism that I had, where I had this little army of students that could go and look at dozens and dozens of images and find loops. Because not only do you want to be able to see the loops, but these loops are sitting in a very substantial background, a field of plasma that looks black on these images, but has substantial intensity. So not only do you have to have an isolated loop, you have to have a very good way to measure the background and be able to subtract it out. So it became more of an observational challenge than to try to do something as a function of solar latitude. So I don't think I'm aware of anyone that's ever tried to do that, but again, I don't know everything that's happening in the field right now. So.
All right, thanks.
Okay, okay, thank you. I have see a second raised hand by Herbert Weil. Hello, Herbert. Willy, could you please open the microphone for Herbert?
Hello,
Yep.
do you hear me?
Yes, we hear you.
Okay, this is okay. Is there any possibility that the solar orbiter mission will shed some light on the heating problem of the solar corona?
I think we all live in hope, right? That is exactly what we're hoping will happen. So I think in the meantime, we work with what we have, and we look to these results from these rocket payloads. But for things like solar orbiter, we're hoping that if they don't solve the problem, at least they give us more insights in which direction to focus our energy.
Right.
Okay, thank you.
Let's move on with the chat. Where were we in the chat? Ritesh Patel has a question saying that AIA 131 passband has a peak at hotter temperatures also, but in your study for the DEM, you consider the cooler component only. Is there any specific reason for this?
Yeah, so we know about the hot component it's a flaring line. So these regions weren't flaring, but it was, even with the material that we were talking about, it was accounted for. So as long as you know where it is, your observations can account for it. So just like for the XRT passbands, they're broadband, they cover a huge range of temperatures. But as long as you know what's in there and you've modeled your passband very well, then you can do temperature analysis with it. So I think the short answer is it wasn't flaring, so it was really dominated by the cool stuff.
Okay. Next question by Mike Brown is the 5 MK you were talking about is electron temperature, I suspect, or he suspects. Are there measurements of the proton temperatures or temperatures of other ions?
So in the corona, those two temperatures tend to be equal because things are in equilibrium. So unless you're at a very, very early stage of a flare, that everything is in like a thermodynamic equilibrium. So it's normally the electron temperatures that we quote, but the proton temperatures are the same.
Right, right. Yes, the freezing in of the ion temperatures of the electron temperatures happens further out. This is the low corona where it's still isothermal. Jim has a comment rather than a question. Jim Klimchuk. Hi, Jim. A new instrument concept, the photon sieve, may allow us to achieve far better resolution than Hi-C in the foreseeable future. Do you have a comment on that? Do you know about the photon sieve? I hear that for the first time.
I don't know about it, and Jim, this is probably some killer question, because I was checking with the updates from Jim just last weekend to make sure I wasn't behind on anything. So he must be a ringer. But Jim, I think we're all looking forward to it. That's that would be my comment. It's like
very good comment.
Resolution,
yes.
like bring it on. Yeah.
Okay. Okay. Angelos Vourlidas has a question. Why aren't the existing and past SXR observations sufficient to establish the presence of the larger than 5 MK plasma? What is missing?
So the idea, the problem is that it's like the temperature dynamic range. So the active region is going to be dominated by plasma around 3 to 4 megakelvin. And these differential emission measure techniques, it's really tough to get that far down to be able to quantify reliably, say, including the uncertainties, how much plasma is there. But there have been observations historically of this hot plasma. They just haven't really quantified everything. So anytime you can observe something like an iron 19 line, That's hot enough to really, really see it. And, you know, we do that sporadically, like with rocket payloads. Okay. So I think MAGICS is really designed to do that differential emission measure and really plow down into what we call, what Amy Weinberger calls the blind spot, this area of the temperature emission measure diagram where we really don't have good constraints on the models. So that's part of what MAGICS is going to give us.
Right. Another question is by Richard Frasin. Hi, Richard. He says almost everybody analyzes active regions for the coronal heating problem. However, the quiet sun corona dominates the low latitude structure at solar minimum. What can you say about quiet coronal heating?
So I think people have claimed to have solved like the quiet sun coronal heating before, right? And it's almost like there seemed to be, for a while, for maybe 10 years, there were a series of papers that appeared in places like Nature that claimed to solve the coronal heating problem, including the quiet sun. And then as soon as they appeared, the community started to try to shoot them down. So in the quiet sun, I think it is straightforward because there's not this hot plasma, there's not this 5 megakelvin plasma. I think it's straightforward to heat that plasma with the AC methods, with the MHD waves. And I'm going to defer to the experts, and I know some of them are on the line, to say what's the latest, like what are the wars going on between the AC group and the DC group currently, and is one dominating? Are they all like second guessing themselves because of the observational constraints? So I don't know the answer of what the state of the art is in the battle between the modelers.
Maybe that relates to the next question, or answers also the next question almost, by Adam Skythe. Regarding the MHD wave heating hypothesis, the AC model, is the global mean MHD wave energy flux into the corona well constrained? How wide is the observational constraint of this quantity?
So I'd say, again, you're way beyond my area of expertise. Okay. I can say that I said that my work on hot plasma was really inspired by a talk at one of the Coronal Lubes workshops, and that talk was by Ad van Ballenhoyen, and he was describing these incredibly beautiful models of MHD waves and how it was effectively heating the corona. But the images that he was using were active regions observed by the X-ray telescope. And I happened to see in his talk that his peak temperatures were between like 2 and 3 megakelvin. And I knew that the XRT images were hotter than that. So that's the question I asked, even naively sort of stumbling into this question. And he sort of stumbled through his answer, admitting that these models did not do a good job of that active region heating. And that's part of why I started working on this particular topic. And I think it's a really nice one because I think I'm gonna paraphrase or quote, or at least paraphrase my colleague Jim Klimchuk, who tells me that this hot plasma is a natural consequence of nanoflare heating models. Yeah. And so it seemed like it was one observable that we could do at the time that could distinguish heating. And we worked on this. Ad went and retired before I could like collaborate with him, but I did collaborate with his colleague Mabube Azugate-Kurte to work on this, and we wrote a couple of papers. One an observational one with her as a co-author, and then her a modeling one with us as co-authors. So I think we try to work on these things, but observational constraints are still tough to come by for coronal heating models.
Okay. Let's move on in the chat. I don't see any raised hands, so let's move on with Julia Galzana's question. Hi, Julia. Where is it? Here it is. Julia writes, I normally find the opposite. Cross sections of the quiescent 1 megakelvin loops are nearly isothermal. The active region core loops are those related to the RTV laws, are unresolved, but also nearly isothermal. Perhaps you could comment on the line of sight issues which can affect the results.
Yeah, so we already talked about the challenges of finding the perfect isolated loop and trying to account for the background subtraction. So I think when you do this analysis, you do it the best you can, you explain it in your paper, you try to do it, 3 or 5 or 7 different ways and come up with the same kind of results. So I think that's what we did. I think it is still possible that we could do it differently or in a more sophisticated way, or if the sun provides the perfect observer's loop, we could do it. But I agree that it does seem like these very cool loops appear to be the ones with the least multithermal plasma. So whether they're at the last stages of cooling, how do we account for temperatures that are cooler than we can observe? They could be there, they might not be there, or they might just be what we can observe as opposed to what the sun is providing.
We have a question by Bill Matthews. Hi, Bill. Is the multithermal character of coronal flux tubes viewed as being a consequence of particle trapping and or suppressed perpendicular diffusion in concert with nanoflares on subsections of the tube?
So I think of it as a simple cartoon type thing where you have incorporated in this loop are magnetically isolated substructures that could be tangled, and that they provide volumes that are isolated from each other. So that that overall the plasma inside one of them could be at a somewhat different temperature and density than the other. Mm-hmm. So I think that's the extent of my sophistication for exactly what the loops might look like, this substructure might look like.
Yeah, further down, there's a comment by Jim saying, yes, energy does not thermally conduct across coronal field lines. I think that relates to this. But Jim further up says that non-thermal light broadening provides an upper limit on the wave energy flux. It is barely enough to explain quiet sun heating, but it is far too small to explain active regions. That's a comment to the previous question and your answer on the AC models. Let's move on. There's a question. There's a question or comment by Helen Mason. Hi, Helen. Can't wait for the next Lubes meeting in 22. Hopefully in person, we can have more animated debates about these issues. And I think that resonates with almost all of us. It's in the in-person meeting where such issues could be debated and discussed and creatively pushed forward in a much more meaningful way than it is possible on these online meetings. And she concludes by, thanks for the good overview, Joan. I think we all agree with that. Jim is very active on the chat. He writes, there is more plasma in the diffuse component of the corona than in observationally identifiable loops. However, we believe for observational and theoretical reasons that the diffuse component is also comprised of many thin strands. That's another comment on the substructure of the loops. Let's a brief question. I'm not sure if I can if what I can make of that, Bill Matthews, is bomb-like diffusion across the magnetic field ignored. I'm not sure if I understand what bomb-like diffusion is supposed to mean, but maybe you do, Joan.
I don't, I'm sorry.
Okay, okay, me neither. Rolf Schlichenmeier comment, great talk, thank you. How can magnetic reconnection in a nanoflare dissipate energy in a way that the entire loop is heated? The whole loops seem to have close to constant intensity visually. Could you comment on this?
So I think the nanoflares are taking place at different locations, on different timescales, and I think one of the observations that you would really want to pin down is the frequency of the nanoflares and their location in the different loops to see, because it's not just one little nanoflare that would be heating up an entire loop. I think it goes back to one of the very early questions. Ever since we've been observing coronal loops, it's related to, well, we have all of these magnetic loop-like structures in the corona. Why are some of them heated up? Why are some of them bright? Why are some of them dark? What exactly is happening to fill some of these loops with plasma that's bright and glowing, and others stay at these very, very low density regimes that don't glow in our observations. So I think this is one of the things that Magix is after, and unfortunately, you know, this talk is sort of right before that first Magix launch, and I'm really hoping that they will find more answers to this. But and the models, let's see, my nanoflare modelers, I know they're on the line because Jim has been chiming in. So maybe he can help answer this question.
Right. Yes, there is a further exchange between Jim and Bill Matthews, which I think you may want to read and connect directly up to them if you want. And in the interest of time, let's try to conclude this discussion. Maybe a last question by Richard Frasin. Is there a standard reference on the non-thermal line broadening indicating enough wave power to heat a quiet solar corona?
I don't know. I mean, the non-thermal line broadening, that was one of those topics that was pioneered back in the 90s by Julie Saba and Keith Strong using SMM data. But I don't know, I really haven't kept up with the current literature, but maybe someone on the chat can type in a reference.
And get back to Richard directly, yes, or type it into the chat, yes. I think we are approaching the end of the 90 minutes maximum, which we have attributed to this talk. So let me thank you once again, Joan, for this very tutorial and beautiful talk, including the discussion. And I think we are all looking forward to two things. Number one, to getting together in person once again, where we can do these discussions over a cup of beer and directly face to face. We are all missing that very much. And number two, we are all looking forward to Solar Orbiter and Solar Probe results, which will shed a lot of new light on these and many other issues. So thanks again, Joan, for educating us in this beautiful talk and for enriching the ISI Game Changers seminar series. Let me remind you for one last time, next week's talk will be on black holes by Reinhard Genzel. And we look forward to seeing you all there. And you have a good night or morning or afternoon or whatever your time zone is. And thanks again, Joan. And I take pleasure in closing the seminar. See you all next time. Bye-bye.
Thank you, Rudy. Thank you, everyone.
Thank you, Joan. This was great. Yes, I really was looking forward to it and I enjoyed it a lot.
Thank you, Joan.
So you have a
from
good
my
day, you
side
have a
too.
long day ahead of you, and thanks very much.